Hello, in this video we're going to look more closely at Euclid and his famous book The Elements. Now, we mentioned this in the video where we created our first description of physics, looking at space and time, saying that we're going to describe space using Euclidean geometry, which is a tricky topic to get your head around, so we'll have a closer look at things in this video. Right, the man himself, Euclid, is a bit of a man of mystery. I mean, he lived nearly 2,500 years ago, around 300 BC. And that's a long time ago, and we don't have much evidence directly about his life. We do know that he spent much of his time in the city of Alexandria, which was Greek at the time. Nowadays, we consider it to be part of Egypt. You can see it here marked on the map. It's on the west side of the Nile Delta. So yeah, nowadays that's in Egypt. But at the time it was Greek. It had recently been founded by Alexander the Great, and he named it after himself. And we know that Euclid spent much of his life living in Alexandria. And that's probably where he compiled the elements. And I say compiled the elements because, as I say, we don't know much about Euclid, and we don't know how much of the elements he actually wrote, how much of it was his own work, or how much of it was a compilation of geometry that was available at the time. So he was probably a part author, part editor of this this book, the Elements, or more accurately, collection of books, because the Elements is actually 13 books combined together into one big volume. And those 13 books cover a range of topics from, say, plane geometry. So that's the geometry, two-dimensional geometry on flat surfaces, a plane, so two-dimensional. So that's your shapes, how you construct shapes, the properties of shapes. Then in the middle books, he moves on to number theory. So what are numbers? What are fractions? What are ratios? How do we count things up? How do we compare these numbers? And then in the final books, he moves on from two-dimensional geometry onto three-dimensional geometry. So solid geometry. And he's looking at solid shapes towards the end. Now, these books are written in a very distinctive style. He creates these lists of definitions, notions, and postulates. So this is saying what things are. So he's defining a whole load of things. What is a straight line? What is a point? So getting right down to the basics of defining what things are. Then he has these notions and postulates, which are statements about the nature of the world. The notions, I think he considers to be, well, at least my understanding is notions are more self-evident, and the postulates are maybe a bit more of a jump, a bit more enlightening, but they serve much the same purpose, that he's stating some idea about the world. And then combining these definitions, notions, and postulates, he then generates propositions, which are theories or methods. So methods of how to construct shapes, for example, or theories and properties such as, say, Pythagoras' theory. So yeah, he's putting those together to get theorems about the properties of shapes and numbers. And this approach, where he's building up from basic definitions and ideas into these higher level explanations, this is what we call an axiomatic approach, and it's very distinctive throughout the book. So let's have a closer look at how this works. So here we've got some of the definitions, postulates, and notions. These are the baseline stuff that he's building everything from. So I've got three definitions at the top here. These first three are all definitions. So he's trying to define a point, a straight line, and a unit. Now, the language that you often see used, he originally wrote all of this in Greek. Euclid was Greek. So it's been translated many times. Obviously, this is translated into English, but it's been translated into English many times throughout history. Quite often, we get left with slightly clunky language. It's because it's quite old. I mean, these are older translations of the definitions. So, looking at the first definition here, a point is that which has no part. It sounds as though we've gone back into Tudor times in order to look at this. There are more modern translations, but these are the ones that you'll quite often see if you get a book on the elements from the library or look online. I mean, we don't need to go into great depths on all of these, but you can say, okay, a point that is that which has no part. So it's something which can't be divided into anything smaller. That's what he's saying a point is. Straight line, he gets, it's even weirder. A straight line is a line which lies evenly with the points on itself. So he's trying to say if we've got a line which could be thought of a whole load of points, then if those points all lie evenly, as in they're not going above or below the path that goes through them, then it's considered a straight line. We might talk about shortest distance between 2 points and things like that nowadays. But this language, it can be useful to think about. It gives you a different way of looking at the world. I mean, this last one here of the definitions that I've picked out is a particular favourite of mine. A unit is that by virtue of which each of the things that exist is called one. I mean, it's like you reassess your whole life reading something like that. And really what it's getting at is, what are counting numbers? So we're talking about units here. If you're counting up the number of cats in the house, 1 cat, 2 cat, 3 cats, well, a unit is, if something that is called one cat is a cat. So that is the unit that we're counting up in. So he's really talking about integers. He's talking about counting numbers here. But it's nice to have your brain stretched a little bit of thinking, well, I've actually really thought about what any of these things mean. Have I ever thought about what a point is, what a straight line is, what a unit is? So he pokes around at those sort of things. So that's definitions, right? Postulates and notions, which are similar. So I've got a postulate here. To draw a straight line from any point to any point. He's saying that this is possible. It's based on this definition of a straight line that he's given. It's possible to draw a straight line between any 2 points, a line which lies evenly with the points on itself. So he's made a statement there, which is down as being a postulate, maybe pushing the boundaries a little bit more than the next one, which is a notion. But you can consider these things to be very similar. Things which are equal to the same thing are also equal to one another. So if A equals B and C equals B, then A equals C. This is, not really, it's common sense, isn't it? And I think that's why he's put it down as being a notion. But off at the back of all of these, and there's loads of them throughout the 13 books of the elements, off at the back of these, he then creates these propositions. So here's the first proposition. So if we go to book 1, proposition 1, he's doing a construction, and he wants to construct what's he trying to construct? An equilateral triangle. That's right. I couldn't remember what he was doing then. So if he wants to construct an equilateral triangle, he marks 2 points. So we've already defined what a point is. You can't divide it into anything smaller. These are just dots. And he's going to connect those points with a straight line. And he's defined what a straight line is. So it matters that it's a point because we've got no ambiguity about where the start or the end of the line is. Now, not like there is on my picture where the dot has quite a lot of area to it. But if you've got an actual point as defined by Euclid, we know exactly where the start of the line is, we know exactly where the end of the line is, and we know that we can draw a straight line on which the points lie evenly with themselves. So we've already used 2 definitions and a postulate just to be able to put those 2 points and a straight line connecting them on the page. So he's done that, and all of these constructions are done with a straight edge rather than a ruler, as in we've got a straight edge, which is a portable straight line. It's not marked out by distance. That's the only thing. It's a ruler that doesn't have, say, centimetre markings on it. It doesn't have any markings. It's just a straight edge. It's just a way of drawing straight lines. And then that actually links in nicely with our, when we're saying we're using Euclidean geometry to describe space, that is one of the things that we're doing, because we've now moved from purely theoretical mathematical stuff. We've now got a straight edge in the world, and we're saying that straight edge will draw a straight line because the world that we're in is flat, in the same way as the paper that we're drawing these things on and formulating these ideas is flat. So we're moving Euclidean geometry into the world. If the world, everything ends up being curved, well, we're not going to be able to draw these straight lines when we're actually doing it. We could think about it, but we wouldn't be able to draw it. So we're moving Euclidean geometry into the world here by having this straight edge. So that's one thing that he's using for construction, straight edge. The next thing that he's using for construction is, well, a lot of people just call it a compass, but if you want to sound as though you come from the Middle Ages, you can call it a pair of compasses and sound, sort of mathematically posh with it all. And this is a way of drawing circles really, and marking on, not just drawing circles, also marking on the same distance in different directions. So what do I mean by that? Well, we're going to see it when we're constructing this equilateral triangle. We've already got one side of the triangle marked out here with these 2 points and a straight line. So if we set our compasses, the width of the compass, we put the point on one of the dots and we set the pencil on the other one of the dots. So we've opened up our pair of compasses so that the extent is the length of that line. We can then mark on a circle based on, say, the left-hand point. So say we were going to now come round and we're going to draw a circle which has the centre of the left-hand point. So wonderful, we've drawn that in. We can now do exactly the same on the right-hand point. So we make that the centre of a circle, and we make the radius the length of this line, just as we did before. And now we've got another circle. Okay, they should be identical circles. This is just with my wonky drawing. Now, these two circles have crossed up here. At least if I'd drawn them properly, rather than doing it freehand, if I had my straight edge and pair of compasses, then they've crossed up there. And we know that we can connect up those 2 points, and we can connect up those 2 points. We know that that length is the same as that length, because they're both radiuses of the left-hand circle. We know that this length at the bottom is the same as that length, because they're both radiuses of the right-hand circle. We know from our notion that if two things are equal to something else, then they're equal to each other. So all of these sides are equal to each other, and we've got an equilateral triangle. So we can see there's a lot going on here. There is something that you might do without giving it an enormous amount of thought of constructing this equilateral triangle is actually built on definitions, notions, and propositions. So this is what he's doing throughout 13 books of hundreds and hundreds of propositions. So yeah, it's a pretty big tome. Now, some people have taken different ways of describing all of this. I mean, it can be quite dry reading the book with the way it's all laid out in this axiomatic approach. One notable variation is Byrne's Euclid. So that's Byrne. So Byrne's Euclid. Oliver Byrne. He was a mathematician from the early to mid 19th century, and he created, I think it was in 1847, he did a version of Euclid's Elements in this beautiful format. He only did the first 6 of the 13 books. He didn't do the whole thing. I'd imagine it gets quite difficult when you get onto the solid shapes. And here's his version of, you'll recognize this as being Pythagoras. So we've got Pythagoras's theorem, which I think is in book 1, is towards the end of book 1 of the Elements. So he's done this using this wonderful sort of color-coded method. So let's read through some of this. So in a right-angled triangle, so he's drawn out the right-angled triangle. You can see it in the picture with this yellow side, red side, black side, and then he's drawn it here in the actual explanation. So he's not using the words to match all of this up and link all of these propositions. He's actually showing the little bits of the diagram. So the square on the hypotenuse, which is the red line. So he's pointing you straight away, okay, this hypotenuse that he's got here is the red line, which is that red line there, which is that red line on the picture. It's equal to the sum of the squares of the other side, so the blue one and the yellow one. So he's stated what it is that he's trying to prove here. This is the end result. And now he's going to go through each one of these. So he's saying for each one of these sides, red line, blue line, yellow line. Yeah, I think they're blue lines. I think I said black line before, but actually they're blue. It's hard to tell. But yeah, I think they're blue. So on each one of those sides, you just draw a square. So square 1, square 2, square 3. Then we're drawing in these dotted lines parallel to each other. So he's drawn in this dotted line coming down here, the black dotted line, and he's drawn that red dotted line going down there. He's also drawn in these two solid black lines. You can see it's so much easier to follow because he's pointing you to the key features on the picture. He's now saying these two angles are equal to each other, so that's that one and that one. We're going to add on that amount. It's the same bit. If we've added on this black angle here to both of those, then they're still equal to each other. And now we've got these two new shapes, which again, you can find them in the picture. So he's building things up this way. I think in these, I won't go through every step because this will take ages going through all of these. These build on as well, which is another reason why I won't do it immediately, but you might want to follow this yourself. It's not that it's that complicated. It's more that these, from memory, these bits here, he's going to start using the results of earlier propositions. So, if this was proposition, I want to say it's proposition 47, but I could be wrong. I might just be thinking 47 because of the 1847 there. But say it was proposition 47 or whatever number it is in book 1. He's used some of the earlier ones. Yeah, he might have used proposition 42, 43, and he's referring back to those. Yeah, again, this is part of the axiomatic approach, that he's building all of this stuff up in this sort of hierarchical way. But I highly recommend reading or at least glancing through Byrne's Euclid and working through, even if it's just Pythagoras' theorem, work through this, see how it works, compare it to other versions of Euclid's Elements. I think all of this is available online if you Google it, or they've got some really nice copies of the books. Okay, I think that's said enough about the book, The Elements itself. It's given a good idea about what it's all about. But before I do finish, I'm going to say something about non-Euclidean geometry, because all of this seems as though, well, everything must be Euclidean. What on earth could go wrong with all of this? Well, two examples of non-Euclidean, if I can say it, non-Euclidean geometry. So let's take spherical geometry. I touched on this before in our description of space. So if you've got curved space, and one example of curved space is if you start doing astronomy and you're trying to work out, you've got various stars in the sky. So that one. We've got 3 stars going around, but the sky, because we're looking at a globe around the Earth, we're looking at a sphere of stars going around the Earth. This isn't flat space. We can't connect these up and say, oh yeah, this is just a plane as in 2D flat space triangle, where if we add up the numbers of the sizes of the angles, they come to 180 degrees. That's not actually the case. Really, this is curved space. So we've got arcs, what they call parts of great circles. which are connecting these points if we're getting the shortest distance between each point. The shortest distance, if you're on a curved surface, isn't a straight line in the Euclidean sense. It's got a curve to it. If you're taking the shortest route from London to New York, it's a curve. You can't say that all of the points lie evenly on the line in the way that Euclid has defined it. So Euclidean geometry won't apply to this if you're drawing these shapes on a curved surface. And things like the sum of the angles won't always, in a triangle, they won't always add up to 180 degrees. So we can't use the findings of Euclidean geometry if we're working on a curved surface. So when you start studying geometry a bit more seriously, you'll have to learn spherical geometry and spherical trigonometry in order to handle the curved surface. Another example of non-Euclidean geometry is what's called taxicab geometry, which you can think of being the geometry of, say, a grid. Say you were wandering around in Manhattan, where the roads and the avenues are laid out on this grid pattern. You've got blocks. So if you started at this point here and you say, okay, well, I want to go a distance of 2 away from where I've started, well, you've got 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. These are all 2 blocks away from where you've started. So they've all got the same radius if you're working on this grid where you have to go in a, all movements have to be in a grid fashion. So you could say this is now a circle in taxicab geometry because the distance of every point is 2 away from the center. So again, we've moved away from the descriptions of Euclidean geometry into a whole new way of describing the world. So there are ways of describing space that are non-Euclidean, but we're making the assumption in our classical physics that everything that's in Euclid's elements, everything that's in flat space geometry is what we can use for the rest of our descriptions in physics. That's what we're deciding, and we can use our straight edge and compasses to construct these views of the world. Right, so I think that concludes. That's quite a lot to take in on all of that, but it's a much deeper look at what we mean by all of this Euclidean stuff.